So in the last lesson, we proved the mean value theorem and went over an example as how to apply the mean value theorem. As we understand, mean value theorem has two conditions instead of three in comparison with Rolle's theorem. And these two conditions are, well, f is continuous and f is differentiable. So the first two conditions, these are the first two conditions of Rolle theorem. So the third condition in Rolle theorem is not needed for the mean value theorem. Okay, so we're going to apply the theorem to our, there are 5 examples I prepared here. So let's look at the first one. The first one is a polynomial on a closed interval. And so it's pretty straightforward because polynomial is differentiable and continuous in its domain. Okay, so excuse me. So solution. Okay, so first we're going to check the condition because we are asked to verify the function satisfy the hypotheses of mean value theorem, which is these two conditions, right? And we just state that, first of all, the function is continuous. Okay, it is continuous on the closed interval. And secondly, it is differentiable. We don't need to prove it because these has been, guaranteed by theorems we have learned before. So this is differentiable in the interval 0, 2. And then we can apply the theorem. Okay, then you just say, then, right? You can type even then, right? Then there exists these numbers exists. You can also say by mean value theorem. There exists the number C between A and B, open interval, replacing A by the number in our situation, such that we're going to plug in the quantities, right? So first of all, we need to know the derivative. So the derivative of this function would be 4x minus 3. And of course, we also need to find f of A and f of B, right? So f of A, which is f of 0, f of B. So f of 0, x replaced by 0, and that's equals to 1. F of B, B is 2, so the x will be replaced by 2 times 2. This will make -5, and that's going to be 8. 8 minus 5 is 3, right? So we're going to plug in all of these numbers. F prime C, right? F prime C, we're going to use this piece. F prime C, so 4 times C, right? F of B equals to 3, F of A equals to 1, and B is 2, A is 0. So we got this equation. So let's organize this equation a little bit and solving for C. So we're going to 4C minus 3, right? 4C minus 3 equals to 3 minus 1 is 2. 2 divided by 2 equals to 1. Okay, so we got 4c, right? Adding 3 on both sides equals to 4, and c equals to 1. C is equals to 1. And then, of course, this c obviously is in the interval 0, 2. So we found it. Okay, so this number, okay, if you like to mention it, it satisfies, right? It satisfies the condition, the conclusions of mean value theorem. All right, so that's it. All right, the second condition, the second question is that we have a logarithm function. In this logarithm function, we need to be aware of the domain because ln x, the domain is x greater than 0. But the good news is that the interval we are considering is inside the domain from 1 to 4, well in the domain of ln x. So we don't have any problem, okay? And then check the first two conditions. Okay, ln x is continuous on the closed interval. And this is guaranteed by the continuity properties we learned in the sections of continuous function. Okay. 2, it is differentiable. All these are, it is also guaranteed in our previous lessons. Okay, so two conditions are satisfied. So let me bring mean value theorem right next to us for easy reference. Okay, then we also need to find a couple of values because we now know the mean value theorem's conclusion applies. So we just have to get all these numbers in place, right? The derivative of the function, the derivative of ln x is 1 over x, right? And f of a is 1, ln 1 equals 0. F of b is 4, ln 4 is equal to ln 2 squared, that equals to ln 2 and 2 times of ln 2. We may or may not need this, okay? But just in case, we have these two forms. You can use ln 4, or you can use the one after we apply the power rule, which is 2 times ln 2. Now, by mean value theorem, okay, there exists number c. C is going to be inside of 1 to 4, such that, so you really just copy this sentence, okay? And put a specified interval to replace a comma b and plug in these conclusions. So we're about to plug in the conclusion. F of b equals to 2 times ln 2, f of a, which is f of 1, and that's 0. And over here is a 4 minus 1, right? 4 minus 1. The derivative is 1 over x, right? That's going to be 1 over c. 1 over c. So now we're solving this equation for c. So what do we get from here? So let's do a little bit simplification. And minus 0, we can drop it. And this is a 3, right? And what does c equals to? What does c equals to? To do, well, we can just flip over on both sides, right? We can just flip over on both sides. So c is equal to 3 would be flipped to the top, 2 times ln 2. So that's what c is. Okay. So that is the mean value theorem which it applies in this example. Here I like to mention something about the geometric meaning of this, okay, or mean value theorem, even though we mentioned that in the theorem proof. So let's look at in our situation. We're going to do a little bit illustration. So the function in our consideration is ln x. Okay, so we're going to draw the function, draw the picture from 1 to 4. Okay, draw the picture from 1 to 4. So this is going to be 5. So this is a negative 1 to, say, positive 2. That should be sufficient. Okay, and line up. So the interval of our consideration is really 1 to 4. Okay, 1 to 4. So we're going to mark that interval. Okay. So this is our interval of consideration. Okay. It's a closed interval for continuity. It's a differentiability for, it's differentiable in the open interval. So this is the interval of our consideration. The endpoints, right? This point is 1, 0, and the other point is 4. So there's another point, which is a 4, 2 ln 2. That's the other point. So that point. Connecting these 2 points, there is a secant line. Okay, so 1, 0, 4, 2 times ln 2. Connecting these 2 lines, this is the secant line. So what this theorem says, we found the number c. This is c. Okay, so on this point c, okay, point c, and the function ln of that number. Okay, what is it, right? So let's simplify this a little bit. The function is ln. Okay, so this point, we're going to plot this point. Oops. We're going to plot this point on the curve. This is the point on the curve right here. What the theorem says, the derivative of the function at this point, the derivative of the function at this point is the slope of the tangent line. So this tangent line passing this red dot in the middle is parallel to this line, to this secant line connecting 1, 0 and 4, 2 ln 2. Okay, I'm going to mark it at some point, but first I'm going to draw the tangent line. Okay, so tangent line passing this point, right? So this is our C, right? This is a C, this is a f of C. Okay, so this is, let me write it down this way. So this is C, f of C. So you understand what I was saying, what we're saying now. And of course, don't worry about how complex this is calculated, right? Usually you don't need to work on this, but you just know this is the point C. C is here, okay? So let me show you. C is cancel. Okay, this is C. Okay, so this is C. Oh, sorry, I probably did not put the dot. This is the C. Okay, this point is C. Okay, this point is C. And this height is f of C. Okay, this height is f of C. Okay, so I'm gonna get prepared to this is f of C is ln that. I should draw, yeah, this is f of C. Okay, so this piece is f of C. So next I'm going to find the tangent line. Okay, usually we now know the slope already, right? The slope of the tangent line is a derivative of the function at the point, right? So the tangent line would be y minus f of C equals to slope, right? What is the slope? The slope is this piece. Okay, that's the slope. And x minus x sub 1. Okay, so that's the slope. And then the line equation will be 2 times ln 2 over 3 times x subtracting when we multiply these two numbers, it's equals to -1. So this is a -1 plus that piece. Okay, so I'm going to draw this line, and that should be the tangent line if I did it right. Okay, that should be the tangent line. I'm going to draw a broken line. There you go. I got it right. I know those numbers looks messy, but I will explain to you just in a little bit. Okay, just in a little bit. So the mean value theorem. Okay, so what we are looking for is this point C. Okay, so now I'm going to mark it with this Zoom software. So in this whole process, this number C is what we are looking for. Okay, this point is C, and this height, right? This vertical line is how high f of C is. So this point, this red dot on here, is C f of C. And passing this point, there's a tangent line. So this broken line is tangent line. This tangent line is parallel to the line connecting the endpoints. So the first endpoint is 1, 0, right? The second endpoint here is is the 4, 2 times ln 2. So this is the whole picture of what we are doing here. Okay, so once we find the C, and we can find f of C, right? So once I find the C, I plug in C into the function, right? I know this look a little messy, just treat it as f of C. So this is C. Okay, so this is C. This is f of C. When we find the tangent line, this is a y minus y1, and the slope, right? Slope, which is the slope by from these 2 points, 1, 0 and 4, 2 times ln 2 times x minus c. So that's how we get the tangent line equation. So this is the tangent line equation. This is a tangent line equation. Okay, this is a tangent line equation. All right. So mean value theorem says, right, if the function is continuous and from 0 to 4 and differentiable between 0 to 4, exclusive, and then there exists such a C inside this interval such that the tangent line passing that point C f comma C, C comma f of C, is parallel to the line connecting the endpoints. Okay, so this is the whole idea of it. You know what? I should do a screenshot of what we did here and put this in our picture. Okay, put it, because otherwise it's going to disappear. It's going to disappear. All right. So this is going to be gone, and I'm going to tidy it up. And here we go. So this is the illustration of this mean value theorem application in here. Okay. And for our particular function, which is ln x. All right. And in the first example, it's similar. Okay, you may like to work on it. If you have any questions, please don't hesitate to reach out to me. That was number 2. Let's look at number 3. Okay. Number 3 is a function. We're going to be it's a reciprocal function. Okay, it's a reciprocal function. Here we go. So the same kind of work we're gonna do. Okay, the function is f of x equals to 1 over x. The domain of this function, of course, x cannot be 0. And luckily, we are given an interval that is very well in the domain. So we don't have to worry about, in between, conditions are not satisfied. So we're going to say, okay, the function is continuous on the interval. Okay. And it is differentiable. It is differentiable in the interval from 1 to 3. Okay, so both conditions are satisfied. So by mean value theorem, okay, so mean value theorem applies by mean value theorem, and we can just say there exist numbers C such that, so it's just really just a copy and paste. Really just copy and paste. However, you need to replace A by 1, B by 3, and we're going to have a following, substitution process. In this substitution, we need to find the derivative. Okay, the derivative can be found from the beginning or when we need it, right? So the derivative 1 over x is negative of 1 over x squared. And f of A and f of B, right? We got f of A. So we got this function, f of A is 1. So f of 1 equals to 1. F of 3. Okay, so that's going to be 1 over 3. 1 over 3. So next we're going to plug in the numbers. Derivative replaced by C. So x is replaced by C. 1/3. And this is 1. So this is 3 minus 1. Okay. And we do some operations here. 1/3 subtract 1 is a negative 2/3 divided by 2. So finally, it equals to negative 1/3. So we come up with negative 1 over c squared equals to negative 1/3. Both sides has a negative sign, so we can drop the negative sign. We'll multiply negative on both sides. And next we flip on both sides. So we get c squared equals to 3. Okay. And then we're going to take square root on both sides. Then take square root on both sides. And then this piece, the left-hand side equals to the absolute value of c, and then equals to √3. And finally, c is equals to plus or minus √3. Oops. Okay, plus or minus √3. Well, negative √3 is not in the interval of interest, right? So negative √3 is not inside the interval of our interest, excuse me. Therefore, the c equals to √3. We found the c. Oops, sorry. So c is equals to √3. So this is the number of our interest. Okay, so by this time the question is done. Okay, so let's do some illustration. Okay, so let's do some illustration. On this illustration, we're going to first graph the function on the interval between 1 and 3. Okay, so this function should be pretty familiar to us. Okay, so between 1 to 3, it has 2 pieces, so we don't have to worry about the other piece, right? So we're just going to drop the other piece and only keep the piece that we want. So this is -5, 5. Let's see if it will work. It will work. Okay, so this is the function we are considering, and we hardly need much of the in the bottom, so it's just probably drop it like this. There. Does this look better? So this is the function. Between 1 and 3, close the interval. Okay. Between 1 and 3. Okay, so this interval of our consideration, and it's a closed interval for continuity. 3, 0. Right there. Okay. And of course, we know this dot and that dot, we're going to connect the dots. I think we don't need this picture to have so much. So maybe just 4, and this is 4. Okay, I just made some adjustment to the picture. And this point is 1, 1. Okay. When at the end point, when a equals to 1 and f of 1 equals to 1, so that dot is right there. Okay, and the other dot, which is 3 at the other end point, which is 3 1/3. So the other dot, we're going to connect these two dots. We're going to connect these two dots. So 1, 1, 3, 1/3. We're connecting these two dots, and there's a secant line. So we found the C. So passing C, so let's plot the C. Where is C? Right? C is √3. At this point, there is, okay, this is C, okay, this is C. So on the curve, when at C, okay, so we want to locate this point, and we're going to draw the tangent line. Okay, we're going to draw the tangent line. So I'm going to make a little bit more changes to the scale. Like this. Okay, so this picture probably looks better. I like this one better. Okay, all right. So this is C and f of C. Okay, so next I'm going to draw f of C. Where's my C? This is C, and we're going to draw f of C. Okay, so right here, f of C is 1 over √C. Okay, so this is the vertical line. Oh, sorry. Where is it? Oh, it should be a line. Okay, so this is f of C. Okay, and this dot, this point is C. We're gonna mark it later. Okay, C. So never mind. So let me do. So this is C. Oops. Where did I go? Okay, so this is C. F of C is 1 over C. Okay, this dot is on the curve, and this is the dot. And there's a tangent line crossing this. There's a tangent line passing this point, past this point, C, F of C. And this tangent line is parallel to the secant line connecting these 2 points. All right, so let's find the tangent line. The tangent line, and of course, we know the point already, right? So the point of C, F of C, what is it? And that's obviously going to be root 3, F of root 3, right? F of root 3. F of root 3, that's 1, well, this is a function, right? So it's going to be root 3, 1 over, don't worry about rationalizing it. Okay, so this is the point right here. And so what is the slope? We found the slope, right? The slope is this number, which is a negative 1/3. Okay, that's the slope. That's a negative 1/3. All right, so now we're going to find the tangent line. The tangent line is y minus, so that equals to the slope. I'm going to put the slope in place, right? So y minus y1, x minus x1. Okay, this is f of c, this is c, that's the slope. So our line equation eventually, our one tangent line equation would be, we got this. Oh, never mind. I should keep it here. Okay. So it's going to be negative 1/3. Oops. To simplify that line equation. Okay, negative 1/3 of x and negative 1/3 times negative root 3. That's going to be plus root 3 over 3. Oops, over 3, right? Because the negative 1/3 times negative root 3. And this piece is adding to the other side. So 1 over root 3 is root 3 over 3. Okay, 1 over root 3 is root 3 over 3. So we have 2 of these, so it's just going to be 2 times. Okay, so that's the tangent line equation. I'm going to plot it in the picture and make a broken line. There we go. Okay, so this is what we are talking about. This is the illustration of mean value theorem. So I'm going to make some more illustration in this picture, okay, with the help of the available tools here, right? So first of all, the interval of our consideration, and this is the point, right? 1, 1, and this is the other point, the end point, 3, 1/3. Okay, so the function is continuous, differentiable as needed by the mean value theorem. We finally find the c. So this point is c, and c is root 3. Oh, I think I'm just going to draw. Okay, so this is root 3. Okay, how about this point? Okay, this point, I'm going to mark it this way. This point, all right. So this point is root 3, comma. Okay, we plug in that function. That's going to be 1 over root 3. So that's the point on the curve. Okay. And so here's the tangent line. So here's the tangent line. So this is the tangent line. This is the tangent line. So this tangent line is parallel to the secant line. So that's what the kind of C we're looking for. All right. So before we move forward with the next question, I think I should take a screenshot of all of these. Okay, so we can keep it in our keep everything in our questions here. So here we go with the illustration. Okay, so we got more. We got more questions to cover. Okay, so I can, let me put this over here. All right, so this is a better illustration of the picture than the other one. Okay, so that was the application of mean value theorem. We have 2 other questions in our plan. Okay, so we're going to work on the other 2. Okay, the first one was, we have such a function show that there's no value of C in this interval such that f of 4 minus f of 1 is equals to the derivative of function as C multiply 4 minus 1. Why does this not contradict to the mean value theorem? Okay, so obviously if the conclusion does not satisfy, if the conclusion is not satisfied, one of it must be not satisfied, right? Because we have learned if A then B, then if not B, then not A. So we have 2 conditions in A, so one of the conditions must not be satisfied. All right, so it says there's no value of C, right? They want us to show there's no value of C such that f of 4 minus f of 1. So we're gonna first show, okay, we're gonna first show that, and then we're gonna go check the condition. We're gonna check the condition. The question is that if obviously one of the condition is not satisfied, okay? If one of the conditions is not satisfied, there's no guarantee such a C would exist. But does that mean that C would definitively not exist? That is actually not necessarily true. It's just we have no guarantee. Maybe it does exist, but there's no guarantee. All right, but if the 2 conditions are satisfied, for sure, the conclusion will be true. So let us show that. So first we're going to find the derivative to show that this one has no solution. Basically, that's what we need to prove, right? So what is the derivative of this function? So this is f. And let's look at what's the derivative of this function. Right, power rule. So we get -2 times x minus 3 minus 1 in the power, and then differentiate x minus 3, that's going to be 1. So in the end, the derivative would be negative 2 times x minus 3 raised to the power of negative 3, right? And so we got that, and we also need to find f of 1, right? Because we needed those for, we need to check if this one has a solution or not, right? So this is f of 1, right? F of 1, replacing x by 1, that's negative 2. Negative 2 to the power of negative 2. What does that equal to? Sorry. And that equals to 1 over negative 2 to the power of a positive. So this is equals to a quarter. Okay, because negative 2 squared is 4. And we also need to evaluate f of 4. Okay, f of 4, we're going to be plugging in this function, x replaced by 4. And this is going to be 1. Okay, so next we're going to plug in. We're going to plug in. F of 4 is 1. F of 1 is 1/4. Right? 4 minus 1, we don't need to do anything. The derivative f prime c, so this function, derivative function, will be replacing x by c. And we're going to solve for c. We're going to solve for c. Okay, so let's solve for c. What do we get? In this equation, we got on the left-hand side is 3/4. On the other side, 4 times 1, that's a 3, right? And 3 times the 2, we can bring the 3 to the front, times 3, right? So why don't you do the 6? Sure, we can do the 6. But I'm not doing it yet. So I'm going to divide both sides. Okay, I'm going to divide both sides. I'm going to divide both sides by negative 2 times 3. Divide both sides by negative 2 times 3. So I'm going to do this on the other side, dividing it. So you can see 3 and 3 would reduce. Now you know why I do that, right? So now the right-hand side would just be c minus 3 to the power of negative 3. And the left, and this equals, and what do we get here? This is going to be a negative 8. Negative 8, 1/8. Okay? And rewrite this as positive exponents. So we're going to get 1 over c minus 3 to the power of 3. Now we got an interesting situation. Okay, there's a negative sign. How about we put it under negative 8, just like that. So we got a situation like the following. Right, remove the middle, which is the bridge. And what does this tell us? This tells us that c minus 3 to the power of 3 equals to negative 8. Okay? And negative 8 is a negative 2 to the power of 3. Okay? x raised to the power 3 function is a, let me write it down. Okay, this will make us related to x raised to the power 3. This function, okay, let us know, what do we know about this function? This function actually is a one-to-one function. Okay, so it has those nice properties, different input corresponds to different output. So this relationship tells us what? They raise to power 3, so c minus 3. So c minus 3 must be equals to -2. And as a result, c equals to +1. C equals +1. C equals to +1. And we want to show there's no value C in this interval such that this is true. Now we found that C is C in that interval. Of course, C is not, because in this interval, C equals to 1 is not included in this interval. So we just have demonstrated, okay? Then we can say that is what? No value C in this interval. Okay, no value C in this interval. So we have demonstrated it because it's right outside. It's right outside. Okay, does this contradict to mean value theorem? Well, let's look at the continuity and differentiability of this function, right? We have found the derivative of the function. So this is the function. Okay, this is the function. I'm going to put it under. Okay, so this is the function. And what's the derivative? We found is the derivative, right? So this is the derivative. So let's look at the domain of the function and its derivative. The domain for the function is x cannot equals to 3. The derivative also says x cannot equals to 3. Domain for both functions in this case, they're not always the same, but in this case, domain cannot, well, any real number but 3. And let's look at the interval of our consideration. The interval in our consideration contains 3. Okay, 3, which is number, so if the function is not defined as 3. Function is not, function is not defined as 3. Right? If it's not defined as 3, then f is not continuous as 3. Oh, I'm sorry. Okay, f is not continuous as 3. And thus, f is not continuous in that interval. F is not continuous on the interval 1, 4, because 3 is right in it. And if f is not continuous, certainly it is not differentiable, right? So we can have, we can say f is not differentiable as 3. As 3, right? So this is a sequence of statements connecting the 3 concepts we learned before, or 2 concepts, continuity and differentiability and their relationship. F is not differentiable as 3, therefore f is not differentiable in the interval. F is not differentiable in the interval of 1, 4. Okay, we need this much to say that theorem does not apply? No, we don't need this much. As soon as you have recognized the function is not continuous on the interval, then the theorem does not apply. But mentioning the differentiability, I just want to emphasize that the relationship between continuity and differentiability. All right, so let's look at the last one. The last one. The last one we have here, it also asking us to show that there's no value of C in 1, 4 such that that is not satisfied. Why does this not contradict to the mean value theorem? And obviously, it's a different situation. Okay, it's a different situation, but the consideration may be similar. In this question, in order to plug in, and we are considering x in this interval. Okay, we're considering x in that interval. So let me just quickly double check. So it's 0, 3. I think the interval I put in there is wrong. It should be 0, 3. All right, 0, 3. Okay, because it gives us a hint here. Okay, so I'm going to put the theorem right here for our convenience. And so here we got the space to work. All right. Between 0 to 3, we have an absolute value. So since the interval of consideration is 0 to 3, and how do we handle this absolute value situation? So let's take a look, right? Let's take a look. In terms of 2x minus 1, this is turned into a piecewise function. Yes, it turned into a piecewise function. So if 2x minus 1 is positive or 0, right? The absolute value 2x minus 1 is the same as 2x minus 1. But if 2x minus 1 is negative, the absolute value of it will be its opposite. We have a negative sign in front of it. So when we have this situation, when we have a function f, and this will be made into two branches, okay? So these 2 branches, we're gonna have 2 minus that, and 2 minus that. Okay, so these are the 2 cases. And we have a point at which, okay, now we can solve these 2 inequalities, right? So 2x minus 1 greater than or equal to 0, so x is greater than or equals to half. and 2x minus 1 less than 0, so that would solve it. X will be less than half. Half is right in between 0 and 3. We have a pointed place, right, which is it's not differentiable. So now we can almost peek into why it does not contradict, because the condition is not satisfied. So this function is certainly continuous everywhere. So the first condition is satisfied, but the second condition is not. Okay, there's a pointed point, but where it's not a differentiable. What is that point? That's half. That point is half. Okay, so there's no problem about the continuity, but there's a problem about differentiability. Okay, so let's continue on this. We're going to simplify this function. So we're going to get a negative 2x plus 1, right? So it's going to be negative 2x plus 3, right? Negative 2x plus 3, because negative times negative 1, that's a positive 1. So we get add to 2, right? And this one here, if we simplify, right? So this negative and negative makes positive, right? So we have 2x plus 1. 2x plus 1. Okay, you can work on your scratch paper to verify that. Okay. So when we take a derivative, okay, when we take a derivative, of the function, right? We're not going to take a derivative at half. So on derivative taking, right, we're going to have just greater than half, because at half is not differentiable. So the derivative at, well, greater than half, a derivative less than half. So we get negative 2, positive 2. Depending on is larger than half or smaller than half. When we are trying to solve this equation, right? When we try to solve this equation, which form shall we use? Shall we use negative 2? Or shall we use positive 2 if we don't know where C is? Where C is. In fact, this is just a constant, right? So we're gonna take a look. Okay. So we're gonna bring this up and put a number in place. What is F? Right? F of 3, 2 times 3. And what does that equal to? That's a 6. 6 minus 1 is 5. 2 minus 5 is negative 3. What is F of 0? 0 times 0. So this is going to be negative 1 in absolute value. So absolute value of negative 1 is a positive 1. 2 minus 1 is 1. So we got the left-hand side. And so to plug in this one, right, to plug in this one, this is going to F of 3 is a negative 3. F of 0 is a 1. And 3 minus 0 is a 2. And what do we do with C? The derivative of C. We either pick negative 2 or pick up a positive 2, right? If it's less than half, we're going to pick up both to see what happens. Okay, so or that. So we're going to put this in negative 2. and they're the same. But if I put in positive 2, if I put in positive 2, right? If I put in a positive 2, this is a false statement, right? This is a false, and this is a true. What do we do? So, in other words, that in this case, it's not possible. It's not possible. In this case, it's identity. It's an identity. So do we have a solution or not? Right? And what is the value C there? It looks like if we plug in -2, so the C possibly be in between half and 3. Okay, so there's a much uncertainty here, but mainly in this case, you can't even apply mean value theorem. Okay, you can't even apply mean value theorem. Okay, so let us double check if I have made any mistake. But this is a situation that this is a situation that doesn't I feel I'm certain about these steps. Okay, for the function in 2 pieces, right? 2 minus that and the derivative, right? So does that mean C exists? We still cannot find the C. Okay, there's no C value. C value cannot be determined. In other words, the value of C, okay, cannot be determined. It cannot be determined. Now the next question is this contradicting to mean value theorem? The answer, of course, is not. Because as we find out, this function is not differentiable at half. Half is inside the interval. Okay, so now let's check the conditions. So we're gonna close pretty soon, okay? In terms of mean value theorem, okay, number 1, the function is surely continuous. Is continuous on the interval, even it's a closed interval 0, 3, no problem. But the function is not differentiable. Is not differentiable at a number at 1/2, which is inside the interval 0, 3. If it's not differentiable at a point of the interval, then it is not differentiable in the interval. Okay, so next we're going to show, that this function is not differentiable at half. This needs to be proved. And of course, we know it's pretty obvious. But we need to prove it. So bear with me. The point of indifferentiability we're going to prove, right? So first of all, the point of interest is f, which is equals to half, right? So this is going to be half is going to replace this x. Okay, so what does this equal to? It equals to 2. Okay, and next will be half plus 8. Okay, it's going to be half plus 8. this will be the perfect opportunity for you to enhance your algebra. So half plus h, half plus h. And you know where we're heading. We're just heading to the definition of derivative. Okay, let's see what we got. We got this piece. All right. And we're going to take 2 times half. That's going to be 1. Right? That's going to be 1. And 2 times h. 2 times h. So inside this absolute value and the function, this is just going to be 2h. We can bring out the 2. Okay. We are getting closer to the definition. So we're going to compose the definition. F of half. Okay, so this is the definition that we are pretty familiar with. Okay, so limit as h approaching 0. Okay, and that equals to, I'm going to show you the original definition. That's going to be A, right? Does that ring a bell? It should, right? So that's the definition we're applying. We are trying to demonstrate that the function is not differentiable at half. Okay, plugging in numbers, plugging numbers. Okay, so this piece will be replaced by that over here. Boom. F of half is 2. So 2 subtract 2, that's going to be 0. So in the end, we got this simpler form, which is the 2's makes 0. So we get -2 times absolute value of h. So now you know that we have to look at the limit from the sides, right? So limit from the left side, when h is approaching 0 from smaller than 0. And that's going to be this limit, right? That's going to be this limit. Since h is negative, the absolute value of h is negative h. As a result, we're going to have positive 2 as the limit. Positive 2 as a limit. And the limit approaching from the other side, which is going to be larger than 0, from larger than 0 side, right? And we put this back in again. H is a positive, the absolute value of h is positive, is the same as h. So this is going to be equal to -2, right? And therefore, what do we say? The limit from left is not equal to the limit from right. And therefore, this limit does not exist. Okay, so that has demonstrated that the function is not differentiable at half. Okay, if it's not differentiable at half, okay, it's not differentiable inside the interval 0, 3, because there's one point it is not differentiable at, and therefore the function is not differentiable in the entire interval. And thus, mean value theorem does not apply. So this example does not contradict to the mean value theorem. We're done. Well, in this discussion, we've done a lot of algebra. Some may look familiar, some look somewhat familiar. So I encourage you to look it over at some point. You can see we use a lot of those things, especially for piecewise function or the absolute value situation. The handling, the dealing and handling of these questions are pretty, similar to a lot of the things we did before, okay? But you can see the original absolute value function is being tweaked to this form. And of course, it still doesn't change the nature of the function. It doesn't change the nature of the function. Last but not least, okay, we're going to check. We're going to show, right, in the examples that the mean value theorem applies or not. And this time we're going to just look at the graph of this function. Okay, so look at the graph of the function to make some sense out of it. Okay, so let's see if we can make some sense out of it. And right, so this is the function we are considering. The interval of our consideration, let me make some more adjustments. This will make it maybe 6. And this maybe 3. Okay. The interval of our consideration is between 1 to 3. Between 1 to 3. So, oh no, sorry, 0 to 3. 0 to 3, my bad. 0 to 3. Okay. Between 0 to 3, so let me draw that so I don't make mistakes. So saying something like that, 3, 0. So on this interval, you can see differentiability is not satisfied. And therefore, we cannot expect the conclusion of mean value theorem would apply. Okay, so mean value theorem only, the result is guaranteed only the conclusion, if the conditions are satisfied. Then you say if the conditions are not satisfied, do we guarantee the conclusion? The answer is no. Sometimes it may be true, sometimes it may be not. And we've seen 2 examples, right? That the conditions in the first example is not continuous. Okay, it's not continuous. The second example is that it's continuous but not differentiable. So in either cases, that the conclusion of the theorem is not guaranteed. Let me know if you have any questions. Thank you for watching.